Hey, Algebra 2 Honor students, this is going to be Functions Day 2. These are notes that are in your packet, and I believe it's on page 17. So if you want to open up your packet to get started, today we're talking about the concepts of domain, range, and also end behavior. So some of these terms might sound familiar. I'm sure you've learned about domain and range in Algebra 1, maybe end behavior might be something new that we add on to the process of analyzing graphs. But before we get started, we have to know ways in which domains and ranges will be represented. And there are three main notations that we're going to see to do this. One of them being inequality notation. We also have something called set notation. And then finally, we have interval notation. So what I want us to practice with just to get started is taking a look at the values that are included on this number line here. And we want to figure out how can I express this specific set of numbers in each of these notations. So we'll start on the left with inequality notation, and I think you'll be pretty familiar with this. We want to include all of the values, inclusive from -3 to +2. So the way that we're going to write that is we're going to say that all of our values x exist between -3 and +2 with those less than or equal to inequalities. So that covers everything, right? If we think about picking any value of x, it could be -3, it could be 2, right? We need those equal to parts because those are closed, filled in circles, and then everything in between. Now, from inequality notation, I always like to do set notation next because it's based on what we just wrote with the inequality notation. It's really just a fancy way of writing an inequality notation using a fancy set of set notation brackets. So we're going to say that the set of numbers and values represented here is the values x, and then draw a vertical bar. That vertical bar means such that. So x such that x is between -3 and 2 with the same inequalities that I used over here. So it's just a little bit lengthier of a statement, but you need to know how to interpret if you're given this set notation right here. You have to know what that means, right? So it's saying all values of x such that x is somewhere from -3 to 2 inclusive. And finally, interval notation. The way we're going to represent interval notation is it's a series of brackets and or parentheses. And I'll tell you when the values are included like they are here at -3 and 2, you will close them off with brackets. So this represents the same set of values as each of the other notations, -3 to 2, with these hard square brackets closing those values in, indicating that we need to include both of those endpoints. And as we go through this, I think you'll see that interval notation probably is the preferred method of a math teacher because it's just less writing. It looks cleaner than the other two. So I shouldn't make you biased right away at the beginning of the lesson here, but just know that if we see these other notations come up, or if we're asked to write something in one of these two notations, we have to at least be familiar with the concept. So it says, a quick note here, this case is a finite interval since it has two distinct endpoints. So if we have one endpoint on either end, -3 and 2, we call that a finite interval. All right, here's another example. So I recommend, for the next one, I already have it filled in. So if you want to take a look, it's similar to what we had up above, but notice how we're only including the left end of this interval at -1, but we have an open circle at 4, indicating that we shouldn't include that value when we list the set here. All right. So see if you can write down the three different notations for inequality, set, and interval, and then I'll show you my answers in a moment here. Okay. So the only difference really being is that since I don't want to include 4, we just won't put less than or equal to for that part of the interval notation. And you'll notice how it's the same thing as up above from number 1, x such that x is between -1 and 4. And then with interval notation, the big difference here is that including -1, we need that bracket again. Since we want to exclude 4, you should use parentheses there. And hopefully this is maybe some notational things that you're familiar with. Okay. Moving on to example 3. So notice for example 3, we now have a set of values that extends in one direction forever. So it's going to be a little bit different. This is no longer necessarily a finite interval, since we have values that go and extend to the left forever and ever. So I'm going to kind of show you one of these at a time. Maybe you already know what's happening here. But for the inequality notation, we're going to say simply that x is, sorry, you guys can't see that. So we're going to say here really just that x is less than or equal to 3. That makes sense, right? This set of values covers everything for x that's smaller than 3. And the set notation won't be so scary either. It's x such that x is less than or equal to 3. So the final piece is, how do we represent an interval notation going to the left forever? I know if we were in class right now together, you'd be all shouting out probably the same answer. Well, going to the left forever indicates that we're heading towards negative infinity. And when you write these intervals, you always want to work from left to right. So something that extends to the left forever, you would start with negative infinity. And then up to and including 3. So notice how I have that square bracket at 3 again because of the closed circle. And note how this is an infinite interval since it's unbounded on one end. Sometimes students incorrectly would write something like 3 to negative infinity because they kind of start here with that number and then work backwards. But you always want to go kind of from least to greatest when you write these. So try and make sure you're accounting for that when writing down some of these intervals. Okay, if we go to the next page, we have some other examples at the top. So example 4. Let's see, I don't even see any stop or end points in number 4, right? So it says, how would you represent this set of values using interval notation? So interval, like I mentioned before, that's kind of my biased preferred of the 3 methods, just because I think it looks the cleanest. Well, we need to represent the values that go to the left and to the right forever and ever and ever and ever. So it seems like we're going from negative infinity to positive infinity. Okay, so a completely unbounded interval in both directions. What numbers are included in this interval? Well, aren't they all? So the way I want you to express this, though, is we're really talking about all real numbers. And all real numbers has a special symbol mathematically. All real numbers you'll sometimes see expressed as a fancy looking capital R, kind of has this extra line drawn there. So mathematically, if you see this, it represents the set of all real numbers. Mathematicians are lazy. We don't want to write down all real numbers. We just want a special symbol that means that. And that's exactly what that R does for us. So now that we see what this looks like here, I'll really challenge you and have you think about example 5. Hit pause for a second and see if you can get the correct interval notation for this set of values on the number line. This one has a little bit of a trick to it, but see if you can get it. Okay, so how are we going to represent this? Well, it really is the same set as above, but I just don't want -2 in the list. So how am I going to do that? Well, I can go to the left forever, so we'll start at negative infinity, but when I get to -2, we have to stop. We have to stop with parentheses. We don't want to include -2. So then how do I show that from there, from -2 on the other side, it goes to infinity? We're going to use this symbol called union. It's kind of this big U that joins these two sets, and then -2 to positive infinity. And this will become a very common way that we'll see notation listed, where we're talking about domains and ranges moving forward. So what numbers are included in this interval? It's everything except 2, or -2, I should say. So you can say all reals except -2. Something like that is sufficient. Okay. So now that we've got that out of the way, I think that will really help us frame our discussion when we get into the topics of domain and range, which are next in our notes. So we have to define domain and range. Maybe you remember what they are from Algebra 1, but if not, I'll give you some quick definitions here. The domain of a function are the set of inputs for which a function is defined. So we're talking about inputs. What we're really talking about are the x values, right? When I input something into a function, it's plugged in for x. So the set of x values, or the set of inputs that define a function, is the domain, and therefore the range is the set of outputs for which a function is defined. So what I want us to be able to do is, based on those definitions, take a look at the examples below. We have examples of things that are graphs. We have a set of ordered pairs in number one, and just identify what is the domain and what is the range. And it does say for the directions here to use interval notation when appropriate. It's appropriate in most cases, I'll tell you, really, except for number one. We don't have a graph that we're given. This is a very distinct set of values. It's not a range of values we're going to be looking at. So for the very first example, the domain of this function right here is going to wind up being the set of x values, -1, 2, and 5. And the way that you're going to write those is by using a curly set of brackets. The curly brackets indicate it's a set that contains only those three numbers. We don't want to use brackets or parentheses. Curly brackets make a big difference here, and they would be required for this type of set. Meanwhile, the range would just be the y values then. So 3, 4, and -8 in curly brackets. There's no requirement that you have to go in ascending or descending order for that matter, so you can just list them as you see them. And that's as easy as it gets for number one, as far as domain and range are concerned. Okay, moving on to something like numbers 2 and 3, well, now we have examples of graphs that are given. So whenever I think about graphs, what I want you to do is kind of hold up a pen or pencil, whatever you're writing with currently. And for domain, since we're looking at x values, the x-axis goes to the left and to the right. So you're really going to scan the graph from left to right side and look at the values along the x-axis for which this graph is defined. Well, based on these arrows, what that's indicating is that this graph actually will go to the left forever, and it's going to head eventually to the right side forever as well. So it's that unbounded interval like we saw up above. The domain for this example in number 2 happens to be in interval notation -infinity to infinity. Okay. So what do we do for the range then? The range are the set of the y values. So here's my y-axis going vertically. So what I'll recommend for the y values, the range, is go from bottom to top. We'll start at the bottom of the graph, and notice how there's nothing existing down here at all. The y values don't really start picking up until the bottom of this U shape. Hoping you remember that this is called a parabola, although it's probably been a while. All right, so we're going to go from bottom to top. The bottom of that U shape is at y equals 3. Hopefully you can tell that pretty easily. But then it goes from 3 all the way up forever and ever and ever. Now keep in mind, we can include 3, right? There's no open circle there that would indicate that we shouldn't include 3. So we're going to do bracket 3 to infinity for the range. And that's a really nice, concise way of listing domain and range in interval notation here. Okay, so moving across the way to number 3, this maybe isn't as recognizable of a graph as parabolas are to us, but just a series of line segments that are connected. And for domain, we're going to do the same thing we did before. Let's scan the x-axis and see what happens. So when I scan the x-axis, oh, we got to stop right here. Okay, that's the first place I see a value along the x-axis, and that x value happens to be at -5. And then we keep scanning, 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 scanning. Up, stop. And that is an x value of 1, 2, 3, 4. I think it looks like +5 again on this side. So with that being said, the domain is from -5 to +5 on the x-axis. But notice how on the left side, this is a closed circle, so I can include it with a bracket. On the right side, we really need parentheses. Meanwhile, the range going from bottom to top, we're going to start with this bottom y value, scroll to the top y value. So at the bottom, the lowest this graph goes is at -2. The highest is 1, 2, 3, 4. Okay, and this is a closed circle. It's not indicated that it's open by any means, so you can actually just put a solid point there if you'd like. Okay, -2 should be included. And at the top end of the range, +4 should be excluded. So that's how you would write the range for that function. By the way, I am calling these functions because they both pass the vertical line test. So that kind of brings in a little bit of info from yesterday. All right, let's go on to the next page. On the next page, number 4, determine the domain only of this function, the square root of x plus 4. There's a couple different approaches you can take here. You can graph it on your calculator if you're really unsure as to what to do, but I want you to think about this algebraically or analytically. We know that domain represents the inputs, right? What am I allowed to plug in for x? So in other words, what is allowed to get plugged in for x? Well, for this specific function, f of x, we can't plug in whatever we want. For example, I'm not allowed to plug in -10 for x. Why not? Because -10 plus 4 is -6, and the square root of -6 does not exist. We can't take the square root of negative numbers. So this will not have a domain of all real numbers. So what's the best way to determine the domain for something like this? And this will come up in future lessons too. The quantity that's underneath your radical, x plus 4, has to always be positive in order for you to take the square root of it, or 0 for that matter. So you can include 0. But essentially what we're looking at here is that the domain, what I'm allowed to plug in for x, has to be such that that quantity underneath the square root symbol, the radical, is positive. Well, this is really easy to solve. Just subtract 4 to the other side, and hey, there's your domain. Done. In fact, it didn't even say anything about interval notation, so you could technically stop here if you want to, right? This is in our inequality notation. So, but just because I do love interval notation, if it's x is bigger than -4 or equal to, you can also list it as -4 to infinity with a bracket. Okay. All right, moving on to the next section here, we have a function f of x defined by 2x plus 1 over x minus 4. We're going to use the table to answer some questions. Evaluate f of 1 and f of 6. So remember, when the input is 1, we're looking for the output, the y value. When I input 1, the output is -1. And when I input 6, the output is 6.5. So that should go pretty quickly if we remember what we did in yesterday's lesson. And the question becomes, why is there an error at x equals 4? Tell me tomorrow in class. I want you to think about that, because that's actually a really important part of identifying domains. And here, 4 is not in the domain of this function. There's an error on the table. Okay. And then state the domain of f of x. Let's talk about that tomorrow too. Okay, I like this question. It's a little bit unique. But let's go through parts B and C tomorrow in class. Let's jump right down to end behavior. End behavior might be new to you this year, but I'll promise it's not so bad. It's the idea that as x increases without bound, in other words, approaches infinity, what does f of x approach? Remember, f of x is the same thing as the y values. So as x goes to infinity, what does y do? On the other hand, as x decreases without bound, approaches negative infinity, what does y do? What does f of x approach? So what we're looking at are the following statements. And when I say to write an end behavior statement, that's exactly what I'm talking about. All these three things are end behavior statements. So you don't have to write any words. It's really all symbolically here. An end behavior statement is as x goes to infinity, f of x goes to what? And as x goes to negative infinity, what is f of x doing? Let's look at it for the first example here. When I say as x goes to infinity, I'm talking about as we go to the right side forever and ever. What are the y values doing? Well, as we go to the right, this graph is heading up forever and ever and ever and ever. So f of x is also approaching positive infinity. Well, what's happening as I go to the left forever, as x goes to negative infinity? As x goes to negative infinity, the graph on the left side is still heading up forever and ever and ever and ever and ever. So f of x goes to positive infinity again. And that's what an end behavior statement tells us, just what's happening at the ends of the graph. Go ahead and take a look at the next example in the middle. So for the second one, we have this graph. Maybe you recognize this type of function. If not, we're going to learn about it this year. As x goes to infinity, so as we go to the right forever, where's the y values going? Well, they're headed up forever. to positive infinity. What if I go the other way as x goes to negative infinity? Are these headed down forever? Not really. I mean, that's not what the graph indicates. It looks like the y values are headed closer and closer and closer and closer to, hopefully you would have answered 0 here. Right, we're getting real close to that x-axis. It almost looks like it touches. I'm not sure it quite does, but it looks like as I go to the left forever, we're getting closer and closer and closer to 0. Finally, in the last example, as x goes to positive infinity, what's the y value doing? So as I go to the right forever, this graph is heading up and up and up and up and up and up. So that's going to infinity. Meanwhile, as I go to the left side forever, the graph is going down, 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 down towards negative infinity. So just a quick look at end behavior statements. This might look a little new for you this year, but hopefully the concept is making sense. I want to do one more example with you. We're going to do number 1 at the top of page 20. And it says for the given graphs below, determine the domain and range in interval notation and write an end behavior statement. So I'm going to do the easy one with you just so you kind of get an understanding of what's happening here. But then I'm going to have you try 2 and 3 on your own, and we'll talk about those in class tomorrow. So just for number 1 here, we're going to talk about domain, range, and then we'll do an end behavior statement. So domain and range, the reason why I think this is maybe a little bit easy to start is just because it's a linear function, right? It's a straight line. And if I think about the domain, the x values goes to the left forever, and this line also goes to the right forever. So the domain is all real numbers, negative infinity to infinity. Talking about the range, the y values, yeah, I mean, this graph's going to go down forever. It's going to certainly head up forever. So the range is the same thing, negative infinity to infinity. Finally, when we get to the discussion of end behavior, it's as x goes to infinity, what does f of x go to? And then on the other hand, as x goes to negative infinity, what is f of x headed towards? So it's almost a statement that you'll have to memorize to a certain extent. If I ask you to identify the end behavior, I expect you to write this down, this information. All right, what's happening as x goes to infinity? When we go to the right forever, the graph's headed up forever. So f of x goes to infinity. As we go to the left forever, the graph is headed down forever. So as x goes to negative infinity, f of x goes to negative infinity as well in this example. So just a little bit of a look as to what you're going to do as a setup for number 2 and 3. I also want you to try domain and range for these, write those end behavior statements. Okay, so try it for number 2, try it for number 3. And next time I see you, we'll go over these 2 in addition to talking about B and C from this question. Do a little bit more practice and then get going on that homework. All right, here's functions day 2. Let me know if you have any questions.